uh, we'll go for the next problem of thin cylinder here. This is the problem number 2 here. Okay, first we will read the problem and we'll try to write the what is the data is given and try to solve the unknown values. Okay, I'll read the problem here first. A 9-meter long thin cylinder. It is a thin cylinder. What is the length of the cylinder here? We'll go data one by one here. That is the data. So its length is, the length of the cylinder is 9 meter, 0.9 meter. That is L equal to, I will go all the units are in mm. So 0.9 into 10 raised to 3, right? 0.9 into 10 raised to 3 millimeter. The length of the cylindrical shell has 450 mm inner diameter. Okay, whatever the inside diameter is there, just d or capital D or small d we can take. Its inner diameter is 450 mm. 450 mm inner diameter and 12 millimeter thickness. Its wall thickness, the cylinder wall thickness is 12 millimeter. That is T equal to 12 millimeter. The cylinder is initially filled with water at atmospheric pressure. Whatever initially the in the cylinder in the beginning, whatever the water is there, it is at atmospheric pressure. Okay, at atmospheric pressure. What you have to determine? You have to determine the pressure at which an additional water of 187 into 10 raised to 3 millimeter cube. It means you are adding the additional water of 187 into 10 raised to 3 millimeter cube may be pumped into the cylinder. Okay, you have to find out the pressure at which extra water 187 into 10 raised to 3 mm cube of water is pumped into the cylinder. The first one is ignoring the compressibility. Here compressibility is one of the factor. First one, you have to find out the pressure when you are pumping the water at this much volume, at this much volume, by ignoring the compressibility. That is the first he is asking here. Okay, you have to find out the pressure by ignoring compressibility. Equal to how much? Next, second one is by considering compressibility. Consider the compressibility and find out the pressure at which you are pumping the water of 187 into 10 raised to 3 mm cube to the cylinder here. Okay, second question he is asking that the pressure at by considering the compressibility is how much. Okay, this is the data is given here. The first one, first we have to, and what are the data again here given? Take E equal to, just we'll note down here, the Young's modulus is given, E equal to 200 GPa. 200 GPa is nothing but 200 into 10 raised to 3 MPa. MPa is nothing but Newton per mm square. Okay, so here two zeros are there, 2 into 10 raised to 5, I will write Newton per mm square or MPa. That is 2 into 10 raised to 5 Newton per mm square or MPa. Okay, next Poisson's ratio is given 0.3 and bulk modulus. Bulk modulus related to compressibility. Volumetric stress divided by volumetric strain. That is the formula. That we'll go through that. That is K. Bulk modulus is 2 into 2.1 into 10 raised to 3 mm cube. Okay, this is the data is given here. Okay, now we'll start. We'll try to start the problem here. The step by step here. Solution. First, we have to assume what is the external volume of the water we are supplying here. 187 into 10 raised to 3. 187 into 10 raised to 3 mm cube of water is pumped at P, at pressure P. Whatever you are pumping, this volume of water is assumed as at pressure P, at pressure P. Okay, now at this pressure when you are pumping, first we will go to the circumferential strain and longitudinal strain. Try to calculate. circumferential strain is nothing but in terms of the stresses, that is circumferential stress divided by E minus nu into circumferential longitudinal stress divided by E here, right? So he's not given any the circumferential stress and longitudinal stress in the data here, right? So we will try to write simplify. What is the formula for circumferential stress here? That is PD by 2T into E minus nu into PD by 2T 4T into E, right? So now here the circumferential strain, put it in terms of whatever the data you know, just fill it here. It is at pressure P, keep it P, and that will be P into diameter is already is given 450 divided by 2 into thickness is given 12 into Young's modulus is given 2 into 10 raised to 5 minus new Poisson's ratio is given 0.3 into P into 450 divided by 4 into thickness is 12 into Young's modulus is 2 into 10 raised to 5. 2 into 10 raised to 5. Okay. This is the circumferential strain. Now keep it the circumferential strain in terms of P, because P we don't know, right? So simplify and put it the circumferential strain equal to 7.97 into 10 raised to minus 5 P. This is one that we need the for further calculation. So that's why I calculated the circumferential strain here. Similarly, calculate the longitudinal strain. That is longitudinal strain equal to longitudinal stress divided by E minus nu into the circumferential stress divided by E here, right? Now again substitute. What is the longitudinal stress here? That is PD by 4T. PD by 4T into E minus nu into PD by 2T into E. So this will be equal to, substitute the values. The P is, how much is there? P is as it is, because we are calculating, we are considered that at that pressure. Okay, P into D is 450 divided by 4 into thickness is 12 millimeter into Young's modulus is 2 into 10 raised to 5 minus 0.3 Poisson's ratio into P into 450 divided by 2 into 12 into 2 into 10 raised to 5. This is this value here. Okay, minus here the longitudinal strain. So now longitudinal, we don't know this one, and P is the unknown value. Therefore keep it as it is. Longitudinal strain is in terms of P. So after simplification, 1.875 into 10 raised to minus 5 P. It is in terms of P. Okay. Now we calculated the circumferential strain and the longitudinal strain. Okay. We know the relation between the volumetric strain and the circumferential strain and the longitudinal strain. Now apply that the equation here. That is the longitudinal strain, volumetric strain equal to 2 times circumferential strain plus 1 time longitudinal strain, right? The 2 times circumferential strain plus the longitudinal strain. This will be equal to 2 into the circumferential strain is 7.97 into 10 raised to minus 5 plus how much is the longitudinal strain? 1.875 into 10 raised to minus 5. This is P, here also P, and this is P, right? This is P. Okay. Now calculate the volumetric strain in terms of P. Therefore volumetric strain in terms of P is 17.82 into 10 raised to minus 5 P. This is volumetric strain. Okay. Now we will go one by one, neglecting the compressibility and the considering the compressibility. First one, we have to calculate the pressure when the volume of the water is pumped by neglecting the compressibility. The first bit is neglecting pressure of water by neglecting compressibility. What happens here? When you supply extra volume of water to the cylinder, you have two factors. One is if you neglect the compressibility, the cylinder volume is increased. It means that is common. When you supply extra volume of water, obviously the volume of the cylinder, it will be increased here. Okay, so if you consider the compressibility, after supply the water, the volume also increase, volume of the cylinder is increased, and due to the compression, the volume of the water is decreased. That you have to take consideration into the second bit. The first bit, neglect that is the pressure of the water by neglecting compressibility. In this condition, when you supply extra volume of water, only the volume of the cylinder is increased. Okay, that we will consider here. So initially, cylinder is filled with water at atmospheric pressure, right? At atmospheric pressure, as per the given data, atmospheric pressure. When we supply extra water, that is additional water, if additional water of 187 into 10 raised to 3 mm cube is pumped into cylinder the volume of cylinder is increased, right? Volume of cylinder is increased. This is very important. Due to additional supply of the water, the volume of the cylinder, volume of the cylinder is increased here. Okay, therefore we have to apply that. That is the volumetric strain. Normally for this one, the volumetric strain by neglecting the compressibility, the change in volume divided by original volume, right? Change in volume divided by original volume. So change in volume equal to volumetric strain into volume here. Okay, so change in volume, how much is there? The extra, if you supply the external amount of water, 187 into 10 raised to 3, it is extra you are supplying, that is increase in the volume, right? So 187 into 10 raised to 3, that is extra volume is changed, equal to, what is the volumetric strain? Just now before we have calculated here in terms of P, that is 17.82. This one 17.82 into 10 raised to minus 5 into P into volume. The volume of the cylinder, you know, that is already diameter and length is there, pi d square by 4. Pi into d is 0.9 into 10 raised to 3. Pi d square by 4 into length is how much is there? D is 450 mm, sorry. This is pi into 450 mm square, 450 square divided pi d square by 4 into length is 0.9 into 10 raised to 3. Okay. Now, so in this equation only one is unknown data, that is P. Okay, P. this is additional volume of water you are supplied to the cylinder, that left side, change in volume. Okay, so now from this equation, P equal to you will get here 7.3 Newton per mm square. This is the pressure. If you supply external amount of extra 187 into 10 raised to 3 mm cube of water is pumped into the cylinder by neglecting the compressibility factor. Okay, now come to the by considering the compressibility factor. Okay, second one, consider by considering compressibility factor. By considering compressibility factor, you have additional volume of water supplied, additional volume of water supply equal to sum of, see, if you apply the compressibility factor, there will be water volume will be decreased and the cylinder volume will be increased. This both will happen at a time, at the same time the volume will be increased. So now whatever the additional volume of water you are supplying is the sum of the volume of the water decreased and the volume of the cylinder increased. Okay, so I will write here the sum of volume of water decreased because compressible factor decreased plus volume of cylinder increased. Okay, so this I will call it as, we know that additional water 187 into 10 raised to 3 mm cube you are supplying equal to the volume of water decrease means change in volume, right? That is the change in volume due to water plus change in volume due to the cylinder. Just keep it this one as equation 1. Now we will calculate this and this in terms of P, then we will find out the unknown value P, then you will get the final answer of the P here. Okay, so due to the water reduction, you have the bulk modulus that is mainly related to compressibility, and that related to change in volume of water, in decrease in volume of water due to compressible. So now we know that the bulk modulus equal to the volumetric stress divided by volumetric strain. That is volumetric stress is normally, that is volumetric stress divided by volumetric strain. Normally this is the formula. If you apply to this problem, volumetric stress is you are applying a P. Whatever P we considered when supplied the water in the beginning, only we took the at the value of P. This extra additional water is supplying, right? So we are taking in the numerator P, this one, and volumetric strain is change in volume divided by original volume. So this change in volume is due to compressibility, and I can write suffix as water due to decrease in the water. Okay, so from this one, the K, already K factor is given. How much K is given? 2.1 into 10 raised to 3 equal to, so P, just put it P, unknown, and the change in volume due to decrease in water divided by original volume we know here, pi d square by 4, pi into 450 square divided by 4 into length is 0.9 into 10 raised to 3. Okay, 10 raised to 3. Now we have two unknown data here. One is P, pressure, and one is the change in volume due to compressibility. Now keep it as it is. If you simplify here, after simplification, you will get here this will be 6.68.1 into 10 raised to 3 P equal to change in volume due to water. Okay, this you have to substitute in this equation here, because this one you just call this one as equation number 1. You have to substitute this one here. Now how about the cylinder increase in the cylinder volume here? Okay, now that already we have calculated the volumetric strain before, the volumetric strain. Okay, the volumetric strain equal to change in volume divided by original volume, already we have calculated here, right? So change in volume due to volumetric strain is, it is because of the cylinder. This is cylinder. Okay, so now you have to substitute the change in volume because of the cylinder equal to this multiply this. Original volume is, just I'm calculating the substituting here, pi d square pi into d square by 4, 450 square by 4 into length is 0.9 into 10 raised to 3. Already we have calculated the volumetric strain here, right? Volumetric strain, that is 17. You just check it before I calculated here, into this 17.82 into 10 raised to minus 5p, 10 raised to minus 5p. We already calculated this one here. Now substitute this value and this value, this one and this one here. Okay, in this equation. Now finally I'll substitute here. We just check it here. Okay, if you substitute in this equation 1, left side is 187 into 10 raised to 3, 187 into 10 raised to 3 left side equal to, so volume of water decreased is, how much is there? Volume of water decreased is, we already just now calculated here, that you have to substitute here. (17.82) this one plus 68.1 into 10 raised to 3p. This we are calculated here. Okay, plus this one plus this one. Now just substitute here. 17.82, this one we are substituting. 17.82 into 10 raised to minus 5p into how much is there? Pi by 4 into 450 square into 0.9 into 10 raised to 3. Okay, so from this one is one factor and this one is one factor. You have to plus it. Okay, if you do this one here, only one is unknown data, that is P. Find out the P due to the compressible factor here. The finally you will get here, that is 2 MPa, 2 Newton per mm square. Okay, this is the pressure by considering the compressible factor. First one we have calculated without considering the compressibility. Now this is with considering the compressibility. With considering, you have to apply at a time both volume of water decreased and volume of the cylinder increased. Apply this equation equal to total volume of water supplied to the cylinder. This how to calculate, I told here, and how to calculate the volume of the cylinder here. You have to calculate both, substitute in terms of P, and this will be the left side is the value. So finally you will get the P equal to 2 into 10 raised to 2 Newton per mm square. Okay.